Righty, ladies and gents, in this video we're going to go over exponential models. Okay, so what is an exponential model? An exponential model has the following equation. The amount of our value that we're measuring after some time t will be the initial amount of that item times e, remember e is the natural base, it's a real number, raised to the k times t power. Okay, so let's define some of these values here. What's A0? This is your initial amount. Okay, remember E is the constant, it's 2.7 and some change. K, on the other hand, is either a growth or decay rate. Okay, so how do we know whether it's a growth or decay rate? It depends on the value of K. If K is positive, then we're talking about an exponential growth model. If, on the other hand, K is negative, we're talking about something that is decaying over time. All right, so think of your bone density. That is decaying as we become older. All right, okay, so let's consider the following. Okay, for example, all right, let's take a look at this question here. Suppose a virus infects 21 people initially on March 13th. By March 26th, we now have 548 people infected. Let T represent the number of days after March 13th. And what they want us to do is find the exponential growth model for this scenario. Okay, so what may be helpful here is to consider, all right, we really have two ordered pairs, believe it or not, with this scenario. We have T, which represents the number of days after March 13th, and then we have the amount of people that are infected, that are sick after T days. Well, initially, so that means time is 0, there were 21 people that were sick. Okay, from March 13th to March 26th, that's 13 days, and then we now have 548 people sick. So based off these two ordered pairs, we can construct an exponential growth model. So here we go. So just to recap, A of t is A0 e to the kt. Okay? All right. So A0, as we said before, that's our initial amount. So I'm going to plug in 21 for A0. Times E, remember E is a value in the calculator, don't you worry about that. It's a natural base. Times K, we do not know the growth rate of this function right now. We're going to solve for it. And then times T, and then we also have to fill in A of T. So A of T represents the number of people that are sick after some time T. Well, there were 548 people that became sick, so we put that on the left-hand side here, after 13 days. So we're going to plug in 13 for T. And so what we have to do here, folks, is we're going to have to solve this equation for K. All right? So first thing I'm going to just rewrite this just a little bit. So 548 is equal to 21 times E raised to the 13 times K. Order of multiplication doesn't matter. All right, to solve for K, we have to solve this exponential equation. So the first thing we're going to do is we're going to divide both sides of this equation by 21. I want to isolate the exponential with the K in it. So on our left-hand side of our equation, we have 548 divided by 21. We're not going to turn that to a decimal just yet. And on our left side of our equation, we have e to the 13k. All right. Now, we're going to exploit this rule. Remember log base b of b to the x. If you recall, when the base of the log is the same as the base of the exponential, the answer is just the exponent. Keep in mind, a natural log is simply a log with base e. Okay, or excuse me. So a natural log is a log of base e, so natural log of x is log of base e of x. So basically what I'm saying is I want to take natural logs of both sides of this equation. So natural log of 548 over 21 has to equal the natural log of e to the 13k. Okay. My left side, let's just keep it in exact form for right now. Over 21 equals, and we're going to apply the property of logs. So remember, the natural log of e to the x is going to be just that exponent x because the bases are the same. So our right side is going to reduce to just 13k. Which means to solve for k, we now divide both sides by 13, and that will give us our exponential growth rate. Okay, so k is equal to the natural log of 548 over 21, whatever that is, it needs to be divided by 13. And let's get this to 3 decimal places. So let's pull up our calculator. Natural log 548 divided by 21. That quantity is then divided by 13. Let's make sure our numbers are correct. 548, 21, 13 looks good. Enter, and there we go. A 0.251 is our growth rate. 0.251. So with all that being said, our full exponential growth model will be a of t equals a0, which is our initial amount, which we said was 21, was the number of people initially affected, times e raised to the 0.251 times t. So what this is this is now an exponential growth model where now we can figure out how many people will be infected for all types of values for t. Okay? And when you have a 0.251 as your growth rate, what we say is that our growth rate is 2.51%. So if you come across your homework and they say, hey, the growth rate is this is a percent, change that to a decimal. And you should know how to do that. Basically, you take 2.51 divided by 100, and that's how you get the 0.251 there. Or excuse me, that's 25. I'm so sorry. That's 25.1% is what our growth rate is there. Okay? All right, here we go. Let's see, I think there's another part here. Yes, how many people will be infected in 45 days? So let me just rewrite our model here. So our model was 21e to the 0.251t. How many people will be infected in 45 days? Remember, t represents the number of days. So all we have to do to figure out how many people will be infected will be plug in. All you got to do is plug in 45 for t. So 21e to the 0.251 times 45. And we're going to use our calculator here. So 21 times e, which is second ln, to the 0.251 times the 45 days. And man, that's a lot of people infected. All right. So then it's going to be 1,688,789. So 1,688,789. All right. That's what happens in an exponential growth model. It grows very quickly. All right. If I had more time in class, I would show you guys something called a logistic growth model. And what that accounts for, it's a more realistic model. And what that accounts for is that after a certain time period, there's not enough people that are going to get sick. All right, and so at some point the virus is going to level off. The curve is going to flatten. So just wanted to keep that in mind in case you're a little worried. All right, how long did it take for the number of people affected initially to double? So this is called double time. So we want to know how long does it take for the initial amount to double. So to see that, what I'm going to do is I'm going to derive the formula for you. So let me go back to our generic exponential model. A of t equals a0 e to the kt. Okay? We're trying to figure out when will this population double. So what that means, I'm going to replace my left side of my equation. I'm going to replace it with 2 times the initial amount, which is a0. And set that equal to a0 e to the kt. So that's what it means to double your initial amount, right? You're 2 times what you started off with. Well, the pretty cool thing that happens here is that I can divide both sides of this equation by a0, and so my doubling time actually has it's independent of how much I started off with, which is a pretty interesting result. So now we have 2 is equal to e to the kt. How long? That means we need to solve this for t. We're going to do the same trick that we did before. We're going to take natural logs of both sides of our equation. On the left side, we have the natural log of 2. On the right side, from our previous theorem that we discussed, or excuse me, the previous rule we discussed, this is going to reduce to just the power because the base of natural log is e, same as that base of that exponential. So the right side becomes just kt. Divide both sides by k, and that is our formula for how we calculate the doubling time of an exponential growth model. So t is equal to the natural log of 2 over k. So if I know my growth rate, I can figure out the doubling time. Or conversely, if I know my doubling time, I can solve this equation for k. But in this case, we know our k. Remember our k was 0.251? So our doubling time will be t equals the natural log of 2 divided by 0.251. Natural log of 2 divided by 0.20. 250. And there we get 2.76. Remember, our time scale is days. So it took about 2.76 days for this population to double from 21 to 42. It took no time to do that. All right. Is there another part here? Okay. So that should get you through that type of question. All right, next question. Suppose the doubling time of a country's population is 45 years. What is the country's population growth rate? All right, so we are going to borrow the work that we've already done. We have shown before that a exponential model's doubling time can be found by this formula. T is equal to the natural log of 2 divided by k. So let's bring that formula down here. T is equal to the natural log of 2 divided by k, where t represents double time. How long it takes an exponential model to double its initial amount. In the health field, there's something called half-life. It tells us how long it takes a material to decay over time. That's what half-life will be. You just replace where it says natural log of 2, you replace with natural log of a half. If I want to know how long it takes my investment to triple in its worth, it'll be the natural log of 3 over k. So it's just replace the argument of your natural log with whatever value you're dealing with. All right, so this time we know t, but we don't know k. So let's plug that into our equation here. So we have 45 years is equal to the natural log of 2 over k. Well, we have to solve this equation for k. So what we're going to do is we're going to multiply both sides of our equation by k. Okay, because I want to get rid of that fraction. So on my left-hand side, I have k times 45, which I'm going to write as 45k. Order of multiplication never matters. And then my, let's close that window. And then my right-hand side reduces to just the natural log of 2. And then lastly, we're going to divide both sides of our equation by 45. And so we get that k is equal to the natural log of 2 divided by 45. My pen is going out. That's weird. Which is approximately, let's see, we're going to take the natural log of 2. We're going to divide that by 45. And we get 3 decimal places. We get a 0.015. So what that means, if I want to write this as a percent, what that means is that the growth rate for this country is about 1.5% per year. That's what that means. But in your homework, I believe they want you to write it in decimal form, not percent form. Okay, one more question. Okay, let's see here. Here we go. Suppose $10,000 is invested at an interest rate of 3.5% and we are compounding continuously. What is the value of the investment after 15 years? All right, so first of all, in a previous video, when we talked about exponential functions, we went over discrete compound interest. Now we're going to get into continuously compounded interest. So the difference is with discrete, we were only calculating interest of a certain number of times throughout the year. Maybe 2 times a year, 4 times, maybe 365 times a year. But with continuously compounded interest, every single moment of the year, we're earning interest. We're earning money. Okay? And so the formula for this is, as you guessed, it's an exponential model. It's A of t, and it's, a lot of people call it PERT. It's P times e to the RT. Okay? Where, once again, P, if you remember your discrete compound interest formula, P represents principal, aka the initial deposit. Okay? R is your interest rate. And T is time. Okay? So yes, folks, this is the exact same thing as A0 e to the KT. Okay? Except for A0 is your initial deposit, K is your interest rate. Because that's how your money is growing based off that interest rate. Okay. So with that being said, let's figure out the amount in our bank account after 15 years. It will be the $10,000 that we initially invested times E raised to the interest rate is 3.5%. Remember to always make your interest rates decimals. So 3.5% is 0.035. Take 3.5 divided by 100. Times T, which is going to be the 15 years. So let's see what that gets us. Let's go to our calculator. Let's clear this out. I'm going to do 10,000. And then second ln is how I bring up my E. And I'm going to raise it to the 0.035 times 15 was the number of years. Just like I said in the previous video with exponential functions when we did discrete compound interest, remember, if your calculator doesn't bump you up like mine is doing, remember to put your exponent in parentheses. So you'd have to put the entire 0.035 times 15 in parentheses. So let me do that now. Insert parentheses. Insert parentheses. So once again, if you're updated like I am here, you don't have to do this, but for my folks that are not, you have to do that. And there we go, 16,904.59. $16,904.59. So that means in 15 years, that $10,000 investment becomes $16,900. All right, folks. This should get you to the homework, I hope. If you have any questions, comments, concerns, send me an email. All right. See you guys later.